this section, we are looking into the flow in pipe networks. Pipe networks have many important industrial applications, like in the oil and gas industry, and also important applications in the water distribution system of in a town, in a building, or in a house. So we can observe here the complexity of a network and an industry. So this is very common when you are refining oil, for example. All petrochemical industry have very complex fluid networks. So the objectives of this video are to identify the main elements in a pipe network, to set up a system of equations needed to solve flow rates in a network. Okay, so let's start to look into the topology of a network. So we can observe this is a network that consists of different pipes. So pipe 1, pipe 5, pipe 2. We can see that the network contains fittings like elbows, T's. It contains probably a pump, a valve, and additionally we are having inlets. So like in this case this is an inlet, Q at A, this is another inlet, and Q at G, this is another inlet. And also we have some points in which the flow is going out, so at D, at B, and at H. So one important thing for a network is that in a steady state the conservation of mass is reduced to the inflows. The sum of the inflows is equal to the sum of the outflows. So we can write this in this particular case like QA plus QF plus QG. So these are the inflows equal to the outflows, which are QB, QD, and QH. Okay, now what else can we recognize in a network? So there are some points in which different pipes are converging. So these points are called a junction. And we have different junctions. So let me highlight the junction in this case. So we have A, B, C, G. We have at E, we have one, and E1 and E2. We have at G, so these are 4 pipes converging, F and H. So in this case we have how many? 1, 2, 3, 4, 5, 6, 7, 8 junctions. And also we can recognize some loops. So the loop are closed circuit that we can have in a network. So this is considered a loop. So flow coming from B and going back to B. And this is a second loop, and this is a third loop. Okay, now in a junction what is important is that we can apply conservation of mass, because we have flow coming into the junction and flow leaving in the junction. So from the junction we have conservation of mass, and therefore we are going to have 8 equations. Now from the loops we have conservation of energy. So in total we have 1 conservation of energy per loop. So in this case we have 3 equations. Now the usual unknown in a network is the flow through each one of the pipes. So we have the equations, and the unknowns are the flow rates. So in this case it will be the flow rate through each one of the pipes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 pipes. So we have 10 pipes, 10 unknown flow rates. So we should have 10 equations. Okay, so if we sum very fast here, we have 8 equations from the joints and 3 equations from the conservation of energy. So in total, you will say, well, you have 11 equations. So yes, we have 11 equations, 10 pipes. So that means that one of the equations will be redundant. And we have to learn how to identify that redundancy. So let's have a look to the junction equations in particular. So let's say that we want to analyze point C. So the junction C. So from junction C, we have an inflow from pipe 1, an inflow from pipe 2, and an outflow from pipe 5. So let me call this F at C. The conservation of mass is going out is positive and coming in is negative. So we have minus Q1 minus Q2 plus Q5, and that should be equal to 0. Right, by conservation of mass. Let's have a look to, for example, B, which is one in that is connected to the outside world, because we have a Q at B that it should be given. So these are the inflows and the outflow should be given. So for B, we have inflows, we have the one from 4, and then outflows, we have QB and we have Q1. So our equation, so negative the inflows minus Q4 and positive the outflows plus QB plus Q1 equal to 0. Now let me highlight that in this particular case, QB is known. So this is not an unknown. So all the other ones are unknown. So, and we can continue with all the others. So we can have the equations for joint A, the equation for joint B, we have C, the equation for joint D, and so forth. So we can have all those equations. So this is a set of equations for the junctions. So in total, we have as many equations as many junctions we have. Okay, before going into the equations for the loops, let's have a look to the equations in a pipe. So we already have done this a few times, but let me consider again a single pipe. So we have from point A to point B, and L is the length, and this is the I pipe. So L, that will be the length of this pipe. So this is the I pipe. So any generic I pipe of the many that we are going to have in our network. So the energy equation for a pipe is the energy here is equal to the energy at this point minus the energy that is lost. So that's the energy at A is equal to the energy at B plus the loss. Now we're going to do some assumptions here. So first of all, the pipe diameter is the same. So diameter in 1 is equal to diameter at 2 by conservation of mass. So then the velocity at A is equal to the velocity at B, and we are going to assume that this is horizontal. So the height at this point is equal to the height at that point. Now that is something to simplify the problem, but we can have different considerations in the network. We can include different heights, something like that. Now, so that means that we are canceling the velocity, we are canceling C, and we just have the PA and PB. So we have PA, the pressure at A, minus PB, so this we move it to the left hand side, and divided by gamma equal to HL. So this is the one that survives, so the loss. So this is the same one. And the loss is formed by two terms. So the loss due to friction and the loss due to the fittings. Now we are going to consider that we have no fittings. So this is 0 if we have no fittings. So in that case, PA minus PB, which is delta PAB divided by gamma, is just equal to the friction term. Now, remember that we can't express this velocity in terms of the flow rate. So the way to do is the velocity is equal to the flow rate divided by the area. And this is for this particular pipe. So the velocity at pipe I is equal to the flow rate at pipe I divided by the area at pipe I. So this is equal to 4 pi, and the area is pi d squared divided by 4. So 4 moves up because it's divided. And when we replace that for the velocity term, so we have that delta P over gamma is equal to the friction factor, which should be particular to that pipe, multiplied by the length of the pipe divided by the diameter of the pipe, multiplied by the velocity square, so this is the velocity square, and divided by 2g. Okay, so that's divided by 2g. So we just simplify, and we end up with this term multiplied by qi squared. So this term is 8 multiplied by the friction factor, the length of the pipe, divided by pi squared, the diameter to the fifth, and the gravity. Now we are going to call this term Ki. Now don't get confused with this K that is the K of the fitting. So this is the K of the pipe. So I decided to use the same K that I use in most of the books. But this K here is defined as, let me write it clearly, Ki equal to 8 multiplied by Fi multiplied by Li divided by pi squared di is to the fifth and g. So this is the K that we are looking. So this is the pipe constant. Okay. Now, having had that term, let's have a look to what happened in a pipe loop. So in a pipe loop, and this is a simple loop in which we go from A, B, C to D and go back to A. So if we want to have a look to the pressure, the drop of pressure in a loop, so we are going back to the origin. So the pressure delta P in the loop is the change of pressure from here to here, delta P from A to B, plus the delta pressure from B to C, plus the delta pressure from C to D, plus the delta pressure from D to A, plus the delta pressure from D to A. Now what I'm going to do is to express these delta pressures, to expand them. So delta P from A to B is PA minus PB, delta PBC is PB minus PC, delta PCD is PC minus PD, and delta PDA is PD minus PA. Now have a look to this. So PB is cancelled with this one, this PC is cancelled with this one, this PD is cancelled with this one, and this PA is cancelled with that one. So delta P in a loop is equal to 0. Actually makes sense. Like, if what is the energy here, if I go around, I should get back to the same energy value in a way. Now We know that this is true, but let me go back to this point. So delta P in a loop is equal to the sum of this, and now I'm going to divide by gamma every single term. And so I'm going to call this is f in the loop is this function, okay, which should be, by the way, equal to 0. And let's be explicit, that should be equal to 0. I just divide by gamma every single term here because I want to use this expression here. Let me highlight the expression. Oh, by the way, you may be thinking, why, if I have qi squared, I'm expressing qi squared as qi multiplied by the absolute value of qi? Well, technically, numerically is the same. So this is the square of qi. But the difference in between these two is that this one will preserve the sign of qi. So that will help the algorithms to self-correct the direction of the flow if you at one point assume that the flow goes in one direction and then the actual flow goes in the opposite direction. Okay, so using this expression, and I'm just going to use the expression delta P from A to B over gamma is equal to K multiplied by QI squared, and this is KI, right? So now when we move to the equations in KI, we just have to take into account the direction of the flow. So I'm going in this direction, so the direction of the loop is in red. But if I'm taking the equation from this point to this point, and assuming that the flow is to the left, so the equation should be negative because it's the drop of pressure should be in the opposite direction, right? It's higher pressure here than there. So that's why we have to include this negative sign. So the next one, we are keep going down, but the direction of the flow is up. So delta P from B to C is minus K2 multiplied by Q2 squared. Now, in this case, it continues going in the opposite direction. So it should be negative. So I should have written this negative here. So that's K3 multiplied by Q3 squared. And the last one is in the same direction. So is the drop of pressure from D to A is K4 multiplied by Q4 squared. So this is the constant of each one of the pipes that we defined previously. Okay, so we can summarize this equation. So the way to summarize it is like this is the sum of all the pipes in the loop. So SI is actually the sign, KI, so the sign that could be positive or negative. So let me put here plus or minus. KI, which is the constant of the pipe, and QI is the flow rate in the pipe, and we just write QI multiplied by the absolute value of QI. Okay, so we have all the possible equations that we can have in a network. Summarizing, in a network, we have junctions and we have loops. For every junction, we have a conservation of mass equation, and for every loop, we have a loop equation, which is conservation of energy along the loop. The conservation of mass equations are written in terms of the directions that we assume for the flow. So for example, in this case A, we have Q4 and Q1 coming in, and coming out is Q4. So QA minus Q1 minus Q4, and that should be equal to 0. And it's the same case for B, C, and D. So we can write the equations. Notice that in the equations that we write, there are going to be some terms that are known, that are the ones that we have in red here, that are the inlets and the outlets of the system. Now for the loop equation, we write in terms of the direction that we assume for the loop and the directions of the flow rate that is assumed. So if they are opposite, the sign is negative, and so like should be in all of these cases, and in positive in the last because they are in the same direction. And the terms are the k constants multiplied by the flow rate square of the pipe. Okay, in summary, in this network we have 4 pipes, 1, 2, 3, 4 pipes, so therefore we have 4 unknowns, which are the flow rate at pipe 1, 2, 3, and 4. We have 5 equations. All the equations are of, we can write it of this form, so it's equation in terms of Q1, Q2, Q3, and Q4, and all these equations are equal to 0, right? We have 5 equations and we have 4 unknowns, so in total we have more equations than unknowns, so that means that probably we have one redundant equation. We can see here, for example, just either C or D. The flow in 3 should be equal to the flow in 2, and the flow in 2 should be equal to the flow in 1. So one of those equations is basically the same. It can be just simplified. One important thing is these are nonlinear equations. So as you have realized in flowing pipes, the flow is in general, the equations are in general nonlinear. We can see here this quadratic term right there. Also, our constant, this is a source of another nonlinearity. This f is also nonlinear, and the f will depend of a single pipe. Okay. Now, so this is an exercise for you. So I want you to write the questions for this section of network. So these are the instructions. So you have to start by assuming the flow direction. So you just know the outflow and the inflow. Okay, and these are the values of the outflow and the inflow. So you have to assume what are the directions. I don't know what are the directions of the flow, and you have to check for the continuity of the entire network. At least that has to comply. Write the continuity equation for each joint A, B, C. Identify each loop and assign a positive direction. So then you have the loop. You say, well, either this direction and that direction, and write the equation. This step 6, you don't have to simplify, so you don't have to do this. So just write this equation. Okay, the next exercise that you have to do is the same with this equation. Now I'll let you do it, and I will publish the result in a second video, so you can actually verify your answer. But please try to do it before I publish, before looking into the video. That exercise is very important for you. Okay, thank you.